welcome back students. So from today we are going to start chapter number 3, and this is the assessment problem 3.1. So here for this circuit which is shown here, we have to find out the voltage across the source, the power delivered by the source, and the power dissipated at around this 10 ohm resistor. So in order to calculate the all the quantities which are defined here or which are given here, first of all we have to calculate the equivalent resistance, and we have to convert this circuit in the form which is feasible, like this one. We have to convert it into this form. So this resistance is called the equivalent resistance. This is the 5 ampere source, so that from this circuit we can easily find out the value of V and the power dissipated by this circuit. Okay, so in part A, the voltage V will be equal to I into R. So this I is given, which is 5, but the value of R is not given. Similarly, for the B, the power delivered to the circuit by the current source. Okay, so this is the current source, and we have to find out the power delivered by this source, which we know that can be found out by this formula. We know the value of I, which is given, but we don't know the value of this V naught. Okay, this is V, or we can also call it V naught. Okay, so to find out these two quantities, we have to convert this circuit into a very feasible form which is given here. To calculate it, the first step will be here, which is converting all the resistors into the equivalent resistance. So here in first step, we know that these two resistors are basically in series with each other. Okay, so its form will be equal to like this one. Okay, let me draw it. So it will be like this one. These two resistors are basically here. This is 16, this is 64, this is 7.2, and this is 30. Okay, I'm not using the omega sign here because it is understood that these are in ohm. So I want you all to know that these are the resistances which are in ohm. The omega symbol is already here, and these are in ohmic form. So now these two resistors, after it, these two resistors are now in parallel. We can see that the 64 and 16 are in parallel, so we have to convert them into the format which will be like this one. Okay, so for calculating the equivalent resistance of these two parallel resistors, we will have 64 plus 16. So from here we will get 12.8 ohm. So it is now 7.2, this is 12.8, and this is 30. This is our source. Similarly, now these two are in series. Writing them in the feasible form. Okay, so now these two are in series, so converting into their equivalent form, we will have 12.8 plus 7.2, and these two will be here. This is a 20 ohm, this is 30, and this is a 5 ampere source. So now we can also see here that now these two are in parallel with each other. Okay, so to find out the equivalent of these two, we will have the R equivalent equal to 30 multiplied by 20 divided by 50, which is equal to 12 ohm. So this is the R equivalent, and now this circuit is of the form which we wanted. So this R equivalent is equal to 12 ohm. Okay, so we have find out the value which we needed. Okay, so after finding out the value, we can put it here, 5 multiplied by 12. So this is now 60 volts. We know the value of V naught now, 5 multiplied by 60. So this is now 300 watts. So we have calculated what we wanted. We have calculated this thing here. So now for part C, we have to find out the power dissipated in this 10 ohm resistor. So there are basically two formulas to find out the power dissipation by any resistor, which are the power dissipation are equal to is equal to V square divided by R, or I square multiplied by R. Now if we have the voltage across any element, we can easily find the power dissipated across that element. Similarly, if the current is passing through the element, we can also find out the value of the power dissipation here. So to find out the power dissipation, we should have the voltage here. So we have to calculate the value of V naught, which is here. So now to find out the value of V naught, we will use the current divider law, which is this 10 divided by 6 plus 10 multiplied by the voltage, which is here. So let me call it V naught double prime. V naught double prime, we have to find out the value of V naught double prime. But the hurdle now is that we don't know the value of V naught double prime. So first of all, we have to find out the value of V naught double prime. So to find out the value of V naught double prime, we have V naught double prime is equal to, this is this resistance. So this resistance is not that this 64, this is the equivalent resistance of the overall. So the equivalent resistance of this overall is now this 12.8, and this is now this 7.2. So we will deploy for V naught double prime, we will deploy this circuit, because now here we have the equivalent of these two resistors. So V naught double prime is equal to 12.8 divided by 7.2 plus 12.8 multiplied by the voltage, which should be here. So the voltage here is, let me call it V naught prime. So V naught prime is not known. Do we know the value of V naught prime? Yes, we have calculated it already, because when we find out the equivalent all of these three resistors which we went here, so this is V naught prime, and we know the value of this V naught prime, which is this small V naught, and we have already calculated it, that is 60 volts. 60 volts, yes. So putting the value here, we will have this 60. So after this 60, we will have the value of it, which is 38.4 volts. Okay, now the value of V naught double prime is known. Let me put it here at the location where it has to be put it. This is now 38.4. So the value when it is calculated is this one, which is the 24 volts. Okay, so the 24 volts is calculated now. So now to find the power dissipation, PD is equal to V square divided by R. The value of V square is 24 whole square divided by this 10. So when it is calculated, it was 57.6 watts. So it is the desired value which is asked in part C of this question. So in this overall question, the overall idea of this question was to find out the equivalent resistance, and the equivalent resistance from a circuit in which many resistances are connected in series or parallel combination. So first of all, we have find out the equivalent resistance of the circuit, and after it we obtained all the quantities which were asked to find in the question. So this was the question, but in this question the overall technique of finding the equivalent resistance from the backside of circuit is formulated. Hello students, welcome back. This is assessment problem 3.2, which is a very interesting problem, and this problem basically illustrates the concept of the loading effect. Here we have a very simple series circuit in which across the 7 kilo ohm resistor a load resistor is connected. So what is it asking us to find the no load value of V naught in the circuit shown. When there is no load here, it means RL is equal to infinity, or it is open circuit. So the RL is not available here, therefore the voltage V naught is all dissipated across 7 kilo ohm, because it is not available here. So now this is a simple series circuit. So in this series circuit we have of the form, now we have 25 kilo ohm, this is 75 kilo ohm, and this is a voltage source of 200 volts. So now to find out the voltage here, which is V naught, which we will use a voltage divider law. So according to the voltage divider law, this is 75k, 25k plus 75k multiplied by the total voltage, which is 200 volts. So V naught here is basically the 150 volts. So this is the value of the V naught when load voltage when load resistance is not available. So this is the actual voltage without any dissipation. Okay, this is our voltage. So now for the other part, find V naught when RL is 150 kilo. So when the value of RL is 150 kilo, when this is 150 kilo, so now we can see that these two resistors are in parallel with each other. So for part B, when these two resistors are in parallel with each other, we have to find out the equivalent resistance of these two resistors, which is 75k multiplied by 150k divided by the 75k plus 150k. So calculating this value, we will get a resistance of 50k. So we can also see here that initially it was 75k. By connecting a resistance of very high resistance, this is 150k is a very high resistance, I mean it is double than this already available resistance. So this is a very high resistance, but by connecting it we can also see the sudden decrease in the available resistance. So when the resistance is decreased, we will also see that the voltage dissipation across this resistance will also decrease. So this is basically the loading effect. Okay, so how is it decreased? How much power dissipates it in the 5 kilo ohm resistor if the load terminal accidentally shorted? Okay, so now we have to find out the V naught when this 50k is the equivalent resistance. So now the value of V naught is now 50k divided by this resistance, 25k plus the equivalent resistance now multiplied by the total voltage here. So by calculating it, we find out that the voltage is dropped to the 133.3 volts. So you can see that initially the original voltage was 150 volts. It is now decreased to 133.3 volts by attaching a very high resistance of 150k. So this is a loading effect. If you have designed a circuit and you are connecting any resistor or load with that circuit, so its resistance will decrease, equivalent resistance will decrease, which will ultimately result in the decrease in the voltage dissipation across that resistor or that load, which will certainly affect the performance of that resistor. So you have to keep these things in mind, and this is also called the loading effect. So for solving the question like this one, the ultimate aim was to let you guys know about the loading effect. So now this is this one. How much power dissipated in the 25 kilo ohm resistor if the load terminals are accidentally shorted? When the load terminals are shorted, so it means RL is 0. When these two are connected in such a way that this terminal is shorted, so all the current will come here and it will follow this route. Okay, the current is coming here and it will follow this route, because now it is the current is following a path which has the lowest resistance, so it will follow this one. So now the circuit we will have will composed of a single source and a single resistor. So the overall voltage will be dissipated across this 25 kilo ohm. So now the power dissipation across this one will be equal to V square divided by R. V is 200, which is all dissipated across this 25 kilo ohm, and its resistance is 25k. So the power dissipation will be equal to 1.6 watt. So this is the solution of part C. What is the maximum power dissipated in the 75 kilo ohm resistor? So the maximum power, it is also a very conceptual statement, because the maximum power will dissipate across this 65 kilo ohm when maximum current will flow uh, through this resistor, and it will only be possible when RL is infinity. There will be no current here, all current will pass through here, and it will be the scenario like which was encountered in part A. So by using the same scenario here, we will find out the maximum power dissipation, which is now 150 whole square divided by the 75k. So the maximum power dissipation here will be 0.3 watts. So this is the maximum power dissipation when the value of RL will be infinity, so maximum current will flow through this resistor. So this is also a very interesting question, which basically described the effect of loading by connecting another load in the design circuit. The all the effects which we can encounter in a circuit are described here. So I think you will grasp these concepts very firmly and will use it in your design process. Thank you so much, and I'll see you in the next lecture.
Hello dear students, I hope all of you will be fine. So this is assessment problem 3.3, in which we have to find the value of R that will cause 4 ampere of current to flow through the 80 ohm resistor in the circuit shown. So this is basically the circuit in which we have to find out our values. So in this condition we have to find out the value of R such that it is telling us that this 4 amps of current is flowing through this 8 ohm resistor. So as these two are in series, their equivalent resistance will be, okay, so this is our input current source, which is of 20 amps. This is 60 ohm. I'm not writing omega here, so if something is written above the resistor, it means it is in ohm. Okay, these two resistors are in series, so their equivalent resistance will be 120, and similarly this is R. So we know this value. This is the 20 amps value, which is the input current. So this is also given that the value here is 4 amps, but the value here, which is IR, is not given. So in order to calculate our required values, let me change the color of my pen. So here we know that in this solution, let me write, it is A. So we know here that according to the KCL, we know that the total current, which is I naught, is equal to the current which is flowing through the 120 ohm resistor plus the value of current which is flowing through this R resistor. So now putting or rearranging it to find the value of IR is equal to I naught minus I 120. Putting values here, we will get IR is equal to I naught is the total current, which is 20 amps, minus the value of I 120, which is given here in our question. So this is now 16 amps. So the value of IR is 16 amps. This is the value which is given here. So after finding it, we can use the current divider law. So according to the current divider law, we know that the value through IR is equal to the value of the resistor, which is at the other end, divided by the 120 plus R multiplied by the total current. So the total current here is 20 amps. Okay, we know all the values except this R here. So putting all the values here, I mean this IR here. So IR is again the value which we have found here. So this is 16. Putting 20, dividing both sides by 20, we will get here 20, and similarly 120 divided by 120 plus R. So after rearranging and calculating the values here, we will find out that the value of R will be equal to the 30 ohm. So this is the value which we needed for the part A of this question. So when we have found it out, what is the second part of this question? This is part B. So how much power will the resistor R from part A will need to dissipate? If we have found out the value of R, so how much power will it dissipate? We know all the formulas for the power dissipation. So to find out the power dissipation here, we know the formula, which is IR square into R. So the value of IR is how much? We have found it out here. This is 16 amps. So 16 whole square multiplied by the value of R, which is 30. So after calculating it, we found that this is 7680 watts. So this is the required result, which is asked to find in part B of this question. How much power will the current source generate for the value of R from part A? So how much current, how much power is it basically generating and passing it to the overall circuit? So in order to find out this, we have to find the equivalent circuit here. So because we know this is the source. So to find out the power generated by the source, we will have this formula: P is equal to IV. We know the value of I, but we don't know the value of V. So to find out the value of V across it, we have to find out the equivalent circuit. In this equivalent circuit, here we know that this was our circuit. So in this circuit, we knew that this was, okay, so it was our circuit. Here this was 60 ohm, this was 120 ohm, and this was 30 ohm, which was found out here. And this is the current source. The value of this current source was 20 amps. So the equivalent resistance here will be equal to the 60 plus 120, which is in parallel with the 30 ohm resistor. So this, after calculating it, we found out the value of R equivalent was 84 ohm. Okay, so this was the value. So when it is found out, we can okay, let me go down. Let me go down here. Okay, okay, so this is R equivalent, and from this R equivalent we can draw a circuit like this one here. Okay, let me rearrange it so that you can easily understand it. Okay, this is our resistor, this is our current source. So this is the R equivalent. So the value of R equivalent is 84 ohm, and the value of this current source was 20 amps. So what will be the voltage here? The voltage here will be equal to V84 will be equal to the 20, which is the series current coming here, and multiplied by the 84. This is almost equal to the it will have some value. So after calculating out this value, we know that, let's suppose this is some value. So after finding out this value, the power dissipation will be equal to IV, putting the value of current here, that is 20 multiplied by, again, this V84. So 20 multiplied by 20 multiplied by 84, that is, putting this value here, it was put down here. Okay, so 20 square multiplied by 84. So the power delivered by our circuit was 33,600 watts. So okay, this was the result. This was the answer of this question of last part in our question. So what did we find out here? This is the overall question. Initially we have started from our circuit. We have found out the value of R, which will assign the value 4 ampere to pass through 80 ohm resistor. Then after it, we find out the power dissipated by this R resistor, which was the 30 ohm, and at the end we have found out the value, the total value of the power, or the total power which was provided by our source. Hello dear students. So this is assessment problem 3.4, and in this problem, okay, let me change it to okay. So this is our circuit now. In this circuit, we are asked to find out some values. Initially, in part A, we have to use the voltage division to determine the voltage V0 across the 40 ohm resistor in the circuit, which is this one. We have to find out this value, which is V0. So in order to find out the value of V0, we will apply here KVL. Let me start it from here. Okay, so applying KVL here, we know that according to the KVL, the source voltage is equal to the value which is dissipated across the 40 ohm, which is V naught, the value or which is dissipated across 20 ohm, and again the value which is dissipated across the V70 ohm. Okay, so let me call this one Vx as well, such that the value of Vx is equal to V20. Okay, so this is our equation, initial equation, and let me call it equation A. So in order to find out the values here, the first thing we have to calculate is the current through these resistors. There are plenty of methods to find out the voltages across V20, V70, because in order to find out the value of V0, we have to use the equation just like 60 minus V20 plus V70. We have to use this equation, and let me call it equation B. So we don't know the value of V20 and V70. Okay, in order to find out the values, we have to find the equivalent circuit. So the equivalent circuit here will be just like this is our resistor, this is another resistor, and this is the third one here. This is 40 ohm, this is now 20 ohm, this is the 70 ohm, this was our source, 60 volts. Okay, this is another resistor which was in parallel with this 20 ohm resistor. This was 20 ohm, and now we can see that the current which will be flowing toward, which will be flowing across 50 ohm resistor will be the same which is flowing to this 10 ohm resistor. Therefore these two are in series and at the back of the circuit. So we will start converting the circuit from the back end, excuse me. When we will convert it, we will see that by adding them together, because two resistors are in series, we will get 60 ohm resistor. Okay, so this is the first equivalent circuit. So after it, we can see that the values of the voltage Vx will remain same here, here, and here. These three are in parallel. So in order to find the equivalent circuit again here, we are simplifying our circuit. So this is the circuit. We are actually simplifying our circuit to find out the unknown quantities. This is 40, this is 70, and this is again 20. So now we can see that these two resistors are in parallel. 30 is in parallel with 60. So when we will calculate their equivalent, this is a 20, and 30 and 60 are in parallel, and their equivalent will also be parallel with 20 ohm, and when we will find out, we will get 20 ohm here as well. So now again simplifying them again, we will get these two are again in parallel. Okay, so by having them in our equivalent circuit, we know that their parallel combination of two equal resistors will be equal to the half of any of the resistors. So here, as we have, okay, so let me correct it. This was again 70 ohm, this was 40 ohm, and this is now half of any of the circuit. Equivalent will be half of any of the resistor, excuse me. So this is 10, this is 40, this is 70, and the value here we have is the value of the voltage source is 60 volts. So this was our circuit, and in order to find out the value of V40, we can use any formula here. One is this one, but we are asked to find out the value of V0 by using the voltage division law. So in order to find it out, we can use the formula which is this V0. So V0 is equal to 40 divided by the 40 plus 10 plus 70 multiplied by the total voltage, which is 60. So now V0 will be equal to this 40 divided by 120 multiplied by 60. So this 62 and this is now equal to 20 volts. So this is the answer of question number question 3.4a. So now in part B we are asked to find out the current which is flowing through this 40 ohm resistor by using the value which we have found out V0, and then use this current and current division to calculate the current in the 30 ohm resistor, which is this one. We have to find out this current, which is, let's say, I0, and then from it we have to find out this value, which is I30. So let me calculate it here. This is part B. So in part B we know that V0 is equal to I0 into R. So as I have told you earlier, that with any resistor or any passive element we have basically three quantities. We connected three quantities, which are voltage, current, and the impedance or resistance of that passive element. If any two of those values are known, we can easily find out the third value. So here, as we know the value of V0, we know the value of R, we can easily find out this I0. The I0 value is V0 divided by R. Putting values here, so that is 20 by 40. So this is now 0.5 ampere. So the value of total current is 0.5 amperes. In order to find out the value of I30, which is flowing through this resistor, 30 ohm resistor, we will use the current divider law. So according to the current divider law, the value here will be equal to, as sorry in okay, we cannot directly find out this I30, but we will go from here. We have find out this value, which is now I0. So this is the I0 here. When I0 approaches here, because why can we not find the required values here? Because once it will come here, there are some other resistors. So in order to calculate it out, we should have another resistor which will represent the overall circuit here. So this should be the equivalent resistor. So as we know that we have already find it out here. So now here the equivalent resistor 20, the other one is 20. These two are the equal resistors. So the current here will be divided into two currents. One current will follow here, the other current will come here. So this current will be equal to, as the two resistors are equivalent, we can see here these two resistors are equivalent, and this is now 0.5. So 0.25 will come here, and the 0.25 will also flow through this one. So this will be equal to the 2.25. This is actually not the I30, but it is I0 prime. So I0 prime is this 0.25, which is flowing through this circuit. So now this is now this current. This is the current which is flowing here. We can see there now this is the equivalent resistance of this 30 and 60. So now we can find out the value which is flowing through this I30 by using this I0 prime. So in order to find out the value of I30 here, we know that here these two resistors are in parallel. So 60 divided by 30 plus 60 whole multiplied by the I0 prime, which was 0.25 amps. Okay, so I30 is equal to, now after calculating all the values here, 60 by 90 multiplied by 0.25. So this is almost equal to 0.167 amps or 167 milliamps. So this is the value which we have found out by using the current divider law. Okay, what were the steps here? Let me repeat it again, as it was somehow difficult. So okay, let me repeat it here. So we have find out this value here, which is I naught, the total current, and we are asked to find out the current which is flowing through this one. As we know that in order to find out the current through any of the parallel resistors, the two resistors should be in parallel. When this current will be used to find out the current here and here, so here we should have the equivalent circuit which will represent the parallel combination of 30 and 60 ohm resistors, and we have found it out here. We know that this is the circuit where we have found out the combination of 30 and 60 parallel resistors. This was our resistance, and from it we have found out the value here which is flowing here, and when we have found it out, this is, we call it I naught prime, and from this I naught prime we then find out the value which is flowing through I30. So in order to find out the value of current here at I30, we consider this I naught prime as the source current. Okay, so this was our part A of this question. Similar part B of this question, and current division to calculate current. Okay, we have found out how much power is absorbed by the 50 ohm resistor. So in order to find out the power absorbed by the 50 ohm resistor, we should have the value of the voltage or current which have been is flowing through the resistor. So this is part C. In order to find out the current through I50, we note that the total current is 0.25. The value current which is flowing through the 30 ohm resistor is 0.167 or 0.16. So I50 is equal to 0.09. Okay, 0.09 amps. So now in order to find out the power dissipated by the 50 ohm resistor, we know the formula, which is I50 square multiplied by R. By putting values here, 0.09 multiplied by the resistor, we know that the value here will be equal to the 0.405. Okay, let me write it here, 0.405 watt or 405 milliwatt, which is the value consumed, or which is which is the power consumed by the 50 ohm resistor. So that's it. This was our assessment problem 3.4, in which we discussed the voltage divider law, the current divider law. I hope you have understood it, and I will see you in the next lecture. Thank you so much.
Hello students, I hope all of you will be fine. So this is our lecture on delta star circuits, that how to solve or find the required quantities in a circuit which are neither in series or nor in parallel configuration. So this is one of the circuits like those configurations, because here you can see that 100 ohm, 125 ohm, these are neither in series nor in parallel, because the two ends are neither connected to each other nor in series with each other. So what we have to do, we have to find the current and power supplied by the 40 volt source in the circuit shown here in this figure. So what we have to do, first of all, we have to find the equivalent resistance, and after finding the equivalent resistance, we have to go towards the current and then power supplied by the circuit. So in first step, what we have to do, this is our circuit here. So in this circuit, this one is, these are our resistors which are given. Okay, this one, okay, these are our resistors. So this is 5 ohm, this is 100 ohm, this is 125 ohm, this is 25, this is 37.5, and similarly 40, and these are connected with a 40 volt source. So in order to find the equivalent resistance, we have to convert any of these two deltas. These two are basically the delta circuits, and converting any of these delta circuits into star configuration will basically make this circuit easier to solve. So let me change the color, and let's say we want to change this delta circuit into the star circuit, because now here you can see that this one and these two are basically the delta circuits. So in order to convert them, sorry, uh, in order to convert them into the delta circuits, let me do it again. Okay, so this one is the first resistor, this is the second resistor, and this is the third resistor, which can be connected here. This is, let's say this is A, this is B, and this is C. So in order to find the values of A, B and C, we have a formula that the value of A can be found out by adding all the resistors which are connected in a delta configurations, and these resistors are 100 plus 125 plus 25. These are all the resistors which will be in the denominator, and in order to find the numerator, we have to look for all the resistors which are connected with this point. So there are only two resistors connected with this junction, and these resistors are 100 and 125. So we have to multiply them together. So when we will multiply them, it will become 12,500 divided by adding them we will get 250. So after finding the equivalent resistance, we will get 50 ohm here. Similarly for B, the denominator will remain the same by adding all the three resistors, which is now again 250. But now for B, the two resistors which are connected with this junction are 25 and 100. So this 25 and multiplied by 100, these two will cancel out, it will again cancel out, and at the end we will get 10 ohm. Similarly for finding the value of C, what we will have, the value of C will be again the denominator will be 250 ohm, and numerator for this one will be 25 multiplied by 125. So simplifying it, 125, this 2 into 25, this will give me 12.5 ohm. Okay, so these are basically the three resistors which we have find out the values. So putting them here and then simplifying the circuits just by removing these resistors. Let me remove these resistors here. So this resistor will be removed. Well, let me remove this resistor and then this resistor. So the equivalent circuit will become like, you can see that here we will have this circuit, which is basically this series circuit, and A and 5 are in series, while this circuit, which is basically the series combination of resistor B and 40, these are again in series, while C and 37.5 are again in series, and the configuration of these two are basically in parallel. So converting them into some unambiguous form, it will become like this one. Okay, so here this is 5 ohm resistor, the resistor A is 50 ohm. Similarly, the value of resistor B is 10 ohm, and the resistor here is 40. The resistor here now we have find out is 12.5, which is the value of resistor C, and similarly this is 37.5. So the equivalent resistance is, okay, this one, this is here, and here this one, this one, these two are now in parallel, and the adding them together, because now these two are in series, these two are in series, and these two are again in series. And in series we know that to find the equivalent resistance, the individual resistances are added. So here it will become 50 ohm, it again becomes 50 ohm, this is now 50, and this is 5 ohm. Okay, so let me go down, let me go down here and solving it here. So now here we can see that this circuit has become this, and the equivalent of 50 to the R50 is equal to 1 over 50 plus 1 over 50, as the two resistors are in parallel. So the R50 will be equal to 25 ohm, because two are in parallel, so their combination will be half of any of them. Okay, so now this is our circuit in which this is 40 volts, and this is 5 ohm, this is 50 ohm, and this one is 25. And at the end, now these three are in series, so in series configuration, adding them together, we will get here 80 ohm, and this is here now 40 volts. Okay, so this is now our equivalent circuit, where 80 ohm is our equivalent resistance. So now here we can easily find out the value of current which is flowing or provided by the 40 volt source. So that is basically, we can find it out by using the Ohm's law. So I is equal to V by R. V is 40 divided by 80, so it is now 0.5 amperes. Okay, so this is the current which is provided by the source. Similarly, the power provided by the 40 volt source is equal to I40 multiplied by 40, which is P is equal to IV. So by using the values here, 0.5 multiplied by 40, so this is now 20 watts. Okay, so this is the overall circuit, and the actual consideration behind solving the circuit like this one is to see that what are the configurations which are neither series nor in parallel combinations, and how to solve the circuits like those ones. So initially we have to find the equivalent resistance, pick any of the two deltas, or pick any one of the two deltas, or any of the stars, and convert them into the other configuration, and you will see that is basically our circuit. And here we have used the conventional circuit laws to find out the equivalent resistance, and after finding the equivalent resistance, we found out the current and power supplied by the 40 volt source. So that's it for today, and we will solve more questions like this one in our upcoming videos. So thank you so much, and I'll see you soon. Hello students, I hope all of you will be fine. So today we are going to solve this assessment problem 3.8 in your book, in which we have to find out the value of this voltage V, in which we are given a 2 ampere source, and there is this circuit which seems like a very complex circuit. So here we can see that we basically, the resistors are connected neither in series nor in parallel configuration. So this is rather a very complex configuration. So we have to sort it out, and then we have to find the value of V by finding the equivalent resistance. After finding the equivalent resistance, we can easily find out the value of the voltage by the Ohm's law. So let's go towards the circuit, and let's demystify this circuit. So this circuit can also be drawn like here. This is also like a diagram of this circuit. Okay, this one, this one. So this is basically the same circuit, in which this is the 28 ohm resistor, this is the 220 ohm resistor, 10 ohm, 5 ohm, and then 105. I'm not writing the omega unit or symbol with these registers for my own convenience. So if you are confused here, so just remember that there is an ohm sign here, okay, omega sign here. So this is the current source of 2 amps. So we can see here that now we have two configurations here. The one here is this delta one and the other one is this steric one. So you can convert any one of these two configurations into the other configuration, and you will see that the circuit will will become very easier for you to solve. So now here let's solve it for this delta circuit. So now here we have this delta circuit. Let us change it into the star configuration. So for a star configuration we will have the resistors in this configuration. Okay, so let's say this is resistor A, this is B, and this is C. So this is now our configuration. So in order to find the value of A, we know that in the denominator we will write the sum of all the resistors in the delta configuration. So these resistors are basically 20 plus 10 plus 28. So these are basically our resistors which are in the denominator, and similarly we have to write the product of all the two resistors which are connected with this junction. So at junction A, at this junction where A resistor is connected, we have two other resistors in the delta configuration which are 20 and 28. So writing 20 and 28 configuration here, so by solving it here, 560 divided by this is 58. So this sum will give me 9.66 ohm. Okay, I have calculated it earlier on. So similarly for B, this is the B resistor, the denominator remains the same and the sum of it will be 58. But for B we have now two resistors 10 and 20 which are connected with this junction where one end of the B is connected. So it will become 20 multiplied by 10. So solving it 200 by 58, and it will give me 3.45 ohm. Similarly for C, denominator again is the same, which is 58, and the product of 28 and 10 will be written because at this junction 28 and 10 are connected. So 28 multiplied by 10, this is 280 by 58, and ultimately the answer of it will be 4.83 ohm. So now we have find out the value of A, for B, for C, and this is the configuration we can sort out. So when we have converted it into the steric configuration, we can easily remove all the delta resistors. So let me remove the delta resistors and see how the configuration will become. Sorry, just removing this. Okay, so now you can see that this is the configuration which is now we have obtained. So after it we can easily convert it into the form which is this one. These are our resistors and this is our source. Okay, so this is our 2 ampere source, this is our resistor A, and the value of resistor A is basically 9.66. this is resistor B, which is basically 3.45. this is the 5 ohm resistor. This is C is 4.83, and similarly this is the 105 ohm resistor. So this is a very simplified configuration, and here we can very easily find out the value of equivalent resistance because now we can see here that this resistor and these two are in series, these two are in series, and writing them in series, and at the end solving it, we will easily calculate the value of this voltage which is here. So again, simplifying it, While simplifying it, it will become these two resistors are in series. So writing a series resistor here, and similarly these two are again in series, these two. So the equivalent resistance here is in series, these two will be added. So 5 plus 3.45 will be 8.45. Similarly 105 plus 4.83, because two are in series, it will become 109.83. Similarly this is 9.66, and this is the source. Okay, so then let us convert them again, because now 8.45 and 109.83, these two are in parallel combinations. Okay, these two are in parallel, so their R prime will be equal to 8.45 multiplied by 109.83 whole divided by 8.45 plus 109.83. So solving it for R prime, it will give me the value 7.85. This is the equivalent resistance of these two parallel resistors. So this is now 9.60, 9.66, and this is that equivalent resistance, which is R prime, and we have found its value, which is 7.85, and the source connected with this one is again here 2 amperes. And simplifying them again, because now in 9.66 and 7.85 are in series with each other, so this will give me an equivalent resistance R equivalent. Okay, and this will be the summation of 9.66 and 7.85, so it will be 7.51. Okay, and the source current is 2 amperes. Now we have to find out this value, which is the voltage here. So we can see here that we have only just one source and one passive element. All the voltage which is generated here is basically consumed by this resistor. Therefore we can easily find out the value of this V. So V is equal to I into R equivalent, and the value of V is therefore I, the value of I is 2, and the value of 7.51. So it will give me the value of V, that is almost 35.01, which is almost equal to 35 volts. Let me write the unit here. So this is 35 volts voltage value which we have obtained from this circuit. So this initially this circuit was very daunting to us. We have converted it into the static configuration, and then after finding out the equivalent resistance, we have found out the value of voltage.